Couple of things off the top. So the Excel assignments due at the end of the week. I'll show you kind of the last stuff that you'll need to kind of complete it today. Actually, I'll probably move that due date. I say probably. I will move that due date after class, actually up until next Monday. So kind of give you throughout the weekend and then all day next Monday to work on that as well, since we're not going over that or everything until today. I'll also put an announcement up on Canvas, but the exam, I'm going to move that date. We're going to do that on November 9th, which is next Wednesday. So we've got one other thing we'll talk about after today, which is hypothesis testing. We'll finish up confidence intervals today, move on to hypothesis testing Wednesday and next Monday. And then kind of also next Monday, I say we'll finish up hypothesis testing. I'll be doing some review on that Monday as well, going into that exam on Wednesday. So November 9th will be kind of that next exam date. If you're looking at some of the practice exams, I'm going to go in and edit them. If you've already looked at them, some of the hypothesis testing stuff, I'm going to hold off on a little bit of it until after this next exam. So you might see those be edited. I'm just adding some of the last few problems for taking out some that I won't expect you to know going into this next exam. Okay. Other than that, I will also put up a Connect assignment that looks like an assignment, but it's actually just practice. It looks like it has points. I can't take the points away the way it's displayed. So it'll say like practice problems or something like that. So it won't be labeled like Connect homework number 4. It'll be practice problems. It's not worth any points. You don't have to do it. I'm just putting it up there for some additional practice if you want on confidence intervals and then hypothesis testing, which I said will start on Wednesday. Okay. All right. So where did we leave off? So we were talking about building this confidence interval. And really like the broader idea of what we were doing is we're trying to create some range of values. So we kind of had our upper and our lower bound. We were centering it around whatever sample evidence we saw and said, well, look, with whatever level of confidence, 90, 95, or 99 were kind of our benchmarks, we can say with that level of confidence, it's within this range, right? The true population mean is somewhere in this range of values. So the way that we did that is we had our sample mean and we added and subtracted what we were calling our margin of error, right? So we were looking up the z value that gave us alpha over 2 on either side of our confidence interval, or alpha total outside of the interval, and then multiplying it by that standard deviation of our sample means. Now, the equation that we had for the standard deviation of our sample means looks something like this. So we said we could break this down into parts, or we could kind of plug in and do it all at once, whatever's kind of easier, just all individual preference at that point. But that's what we were doing. Right? And I showed you kind of some examples in Excel. So today we're going to look at just a very unique case of the sample mean, which we've already talked about, which is the sample proportion. Right? We said the sample proportion is just a sample mean, but of a 1-0 variable. So we're going to do the exact same thing for sample proportions. And we're going to build a confidence interval where the true population proportion is based off our sample. So we're no longer looking at the sample mean, we're now looking at the sample proportion. But we know that sample proportions, we can turn those into z values as well. So they should also be standard normally distributed. So we're still going to use the same process and look up how many standard deviations away do we want to go to get alpha over 2 on each side of our interval. And then we're no longer looking at the sample mean, so we can't multiply by the standard deviation of our sample mean. We're going to multiply by the standard deviation of our sample proportion, which if we go back, that was the square root of population proportion times 1 minus the population proportion divided by the sample size. But we run into a problem here. The whole reason I'm building this confidence interval is because I don't know the population proportion. So when it comes to confidence intervals, we're just going to use our best guess of what that is, which is using our sample proportion. So I think I've got we've talked about this already, right? With these 3 benchmark kind of confidence levels, 90, 95, 99, or sorry, 90%. We figure out alpha by its the decimal form of what's outside of our interval. So 99, 1% will be outside, alpha is 0.01. 95, 5% outside, alpha is 0.05, et cetera, et cetera. So we kind of typically find that because we're looking at these same benchmark values, alpha is going to always be 0.01, 0.05, and 0.1. So when we divide it by 2, it's always going to be the same value. When we go to the table, when we look up those values, we'll always find the same corresponding z values. Those typically tend to be, right, 90%, 1.65, 95%, 1.96, and 99%, 2.58. These other two that I have up there are some that we'll see pop up once we get to hypothesis testing. But for now, at confidence intervals, these are going to be the ones that we kind of see pop up the most. Right, so we'll start seeing them happen a lot. There's a reason why. Well, it's because we're always using the same benchmark values for confidence, which gives us the same benchmark alphas. Once we look up those alpha values in the table, we're always going to find the same corresponding z value. So I kind of already went through this on the board. We're going to have to estimate what that, we don't have the population proportion, so we're just using the best guess, which is the sample proportion. But really from there, and that requirement is just me being kind of complete. It's saying something about if we have really low probabilities, we need to make sure the sample size is a certain size. I can never try to trick you or anything like that. Everything we'll look at will kind of have that satisfied. So we've got very similar setup. Now on here, I wrote kind of plugged in that standard deviation is my sample proportions. Like I said, you can calculate this separately, then just have one value plugged in. And here is where, before I said calling this the margin of error was technically not correct. You're really only supposed to use that when we're kind of talking about proportions, but it's kind of semantic, so it just makes it easier to think about. The thing you're adding and subtracting, no matter what statistic you're looking at, will just reference to the margin of error. Okay? So looking kind of familiar, like we've talked about this sample proportion distribution already. So let's start to kind of work through a problem. It's really building these confidence intervals, exactly what we were doing last week, with just kind of this added wrinkle, which is the standard deviation is calculated a little bit different. Okay? So let's say I've got an example where some old polling data about Obamacare, and 63 out of 81 respondents were in favor of covering pre-existing conditions, and we want to build a 99% confidence. So this is one where you're not directly given that sample proportion, but how can you calculate it? You want the proportion of people who are in favor of covering pre-existing conditions. Yeah, it was just 63 out of 81 individuals. So I think if we break this down, this is what, 7/9. So we've got our sample proportion, and we get to use the decimal value we want to. And I want to build a 99% confidence. So here, 99% confidence, what do I want alpha to be? So alpha is the decimal form. 0.01. Yeah, 1% is outside the interval, so 0.01. And then my sample size is asking me 81 individuals, so 81. Okay. So that's really all I need. All right, I can plug in my sample proportion, sample size. The only thing left I need to find is just to look up that z value. So what z value do I want? I want the z value that would give me alpha total in the tails, which means that there's half of alpha in each tail, or what? 0.01/2 is 0.005. So I'm going to go to my table, which I think I might have accidentally exited out of when I had it open earlier. So we'll see if it's still up. Sweet, I didn't. All right. So I've got my standard normal distribution table. I know the area I want in the tail is 0.005. So I have the probability. I then want to find the corresponding z value. So I'm going to be looking in the middle here for 0.005. Looks like it's in between these two values. So negative 2.57 and negative 2.58. We'll use the higher of the two, or the larger in magnitude. So here, we just found that z value, or the number of standard deviations the way we want to go, is 2.58. Right? We'll add that many standard deviations to our sample proportion to get our upper bound. We'll subtract that many standard deviations to get our lower bound. All right, so we can do the intermediate step here, which is, I wanted to use this version of the formula where I kind of break it down into steps. I always said this is the square root of my sample proportion times 1 minus that sample portion divided by my sample size. So at this point, it's just a matter of getting that entered in my calculator. Sorry, this is probably hard to read. 1 minus 7/9. There we go. So if I do that, I get about 0.046. Well, that makes my life a little bit easier, because now I only have one value to plug in here. I know my z value is 2.58, my sample proportion 7/9. So now it's just a matter of getting that all entered into my calculator. I've got the 3 values I need now. Just plug them in, add that margin of error to my upper bound, subtract it to get my lower bound, and I get what? 0.66 to about 0.9. Rounding pretty bad there, but. So how can I use this confidence interval? If I'm thinking about the context, I go back. We're thinking about who is in favor of covering pre-existing conditions. So when I'm looking at this confidence interval with 99% confidence, right? I can say that the true proportion of people in favor of supporting covering pre-existing conditions is somewhere between 2/3 and 90% of people. If I'm a policymaker, a politician, like I look at that, I'm like, oh, well, this should get through no problem, right? Everybody, you know, the vast majority of people are in favor of this one aspect of Obamacare. Right? So you know, if you tell me like, you know, more than half the country is not in favor of it, I could tell you, no, that's not the case at all. Any questions kind of over anything in this topic? So hopefully it's kind of looking familiar. It looks a little bit like what we were doing before. Equations just changed a little bit. So I want you guys to try to kind of work on this one on your own. And just to kind of get an idea of where we're at with this. I'll use it as an iClicker question for the day. For those of you who are here. So if I went out and polled 912 people, so this was from the, I think, 2016 election. There's this huge poll, and they found 46% of people said they were going to vote for Clinton. And you wanted to come up with a 90% confidence interval for what the true proportion of people who are going to vote for Clinton is. Okay? So, excuse me. What I'm thinking about here is 46% of people said they'd vote for Clinton. So that's going to be my sample proportion. I have to do a little bit of work to turn a percentage into a proportion. We generally talk in terms of percentages, but here we're going to build this for a proportion. So 0.46 should be my sample proportion. Hopefully we can figure out our sample size. We want the 90% confidence interval. So figure out what kind of alpha that corresponds to. And look up that z value that we give you alpha over 2 on each side. And then it's just a matter of plugging in kind of what we know. That sample proportion, our sample size, and that z value that you find. Okay. So I'll give you a little bit of time to work on that. Once you talk to people around you, just kind of hopefully run or see what kind of problems we run into kind of working through this.
What do we do for the first 2 minutes of class?
I kind of just reviewed what we talked about last
Okay.
week, right? And then kind of this is kind of relating this to what we did last week.
And are we having connect assignment for confidence intervals?
So I said I'll put up a practice. It's not an assignment for points. It's just additional practice problems going into next week's exam, which will be on Wednesday. And I'll put a Canvas announcement up about both of those. we'll talk through this one together. So I want to build this confidence interval, right? So kind of got the equation over there. I'm going to center it around what value? Yep, it's going to be centered around my sample statistic or my sample proportion of 0.46. If I wanted to know what alpha is here, the 90% confidence level, what is alpha? 0.1, right? It's the area outside of my confidence interval, but in decimal form. But I know that I'm actually need to look up the z-value that gives me half of alpha on each side. So if I think about what's half of alpha here, 0.05, I've got 0.05 on each side. So if I look that up in the z table, what's the corresponding z-value I find? 1. Yeah, I'm in between 1.64, or well, negative 1.64 and negative 1.65. I have to remember that negative sign's already kind of built in there, right? I'm looking for the number of standard deviations to the left and the right. I'm always going to find the number of standard deviations that need to go to the left with a negative value. So when I plug it in, I really just need that 1.65. So 1.65. Now, if it were me, from here, I'd break this down. I know that I should be multiplying by that standard deviation of my sample proportions. If it were me, I'd go ahead and calculate that first. So 0.46 times 1 minus 0.46 divided by that sample size of 912. Does anybody come up with this? Do they break it down in steps or just do it all at one time? 0.0165. That's what I remembered as well. My memory is not perfect. So 0.0165 should be that standard deviation. Now you just have one value to plug in up here, and we should be done. Right? So come back to these answers, right? Kind of our benchmark value, sure enough, when we wanted 0.9 in our confidence interval, alpha over 2 on each side led us to that 1.65 value. We identified the piece of information we're giving, looked up that z-value, calculated this intermediate step, and now it's just a matter of plugging those values into our calculator, right? Adding our margin of error to the upper bound, subtracting it to the lower bound. 0.4328 and 0.4872. 0.328, 0.4872. Hopefully everyone's getting this one correct. I haven't closed it out, right? So make sure you're kind of getting a response in here. You just kind of work through and found what that lower and upper bound are, right? All right. Everybody make sure you get a response in. All right, there we go. All right. So, right. That's kind of the steps that we use. Are there any questions before I keep moving here? So I'm going to walk you through a couple of examples. We're going to go through pretty quick. They just have different numbers just to make a different point. I'll then kind of show you how we do this in Excel, and then we'll kind of go to our next kind of final confidence interval, which is sample means. When we don't know the population variance, all we have is a sample variance. One little thing changes. So I thought this was kind of interesting just to go through this one. But I have polling data. This is what they actually do. Let me see. I go back too far. Yeah, so this is from the last selection. So this one maybe is a little bit more relevant and interesting. Some of you are probably pretty young still, I guess, in 2016, probably don't really care that much. So the last selection, right? There was, I think I grabbed this from the one that got it correct in 2016. So this is Reuters data. So it's almost 1,200 people, right? They polled, and they found that 54% of people were going to plan to vote for Biden. So we could build a 90% confidence interval for that. It's going to be the exact same thing that we had in the previous problem. The only thing that changes is our sample proportion, our sample sizes are different values. But it's the 90% confidence level. So if we divide alpha by 2, look that up in the table, sure enough, we find the exact same thing as before. Right? That z value that corresponds to alpha over 2. Well, when alpha over 2 is the same, we're going to find the same z value. So I build this out and I get 0.51 to about 0.56, just to kind of make my point here. So the true population proportion of people who are going to vote for Clinton could be anywhere in this range. Okay. From that same poll, that same survey, I found the sample proportion of people who are going to vote for Trump was what? 43%, or at least the people that said they would. I do the same thing, my sample proportion value is a little bit different now. Still going the same number of standard deviations away, except with that 90% confidence interval. But now I've got what, about 0.4 to 0.45. And the true population proportion of people who are going to vote for Trump, somewhere in this range. Okay? So what's interesting here is I can actually, when I construct these two confidence intervals, and this is how they make predictions going into elections, I can tell you with 90% confidence who's going to win that election, or at least the popular vote. Well, even if the population portion of people who vote for Trump was at the highest limit, the upper limit of this confidence interval, and Clinton's was at the very lowest, what's true? Population portion of people who vote for Clinton, 90% confidence we could say is going to be greater than that of Trump, right? So if you don't have any overlap in your confidence intervals, you can say that one group is going to have, you know, a larger mean than the other, or you could say here, one candidate is going to get a larger proportion than the other, right? Now, I want to actually predict elections, I'd have to like break this down by state, do surveys with each state, and then do the, you know, figure out the electoral college numbers. But this is essentially how they kind of make these predictions. And whenever you hear them talk about, like during elections, they'll be like, yeah, they're polling at, oh, what was this, 46% plus or minus something, right? Or I guess, sorry, this was 43, just imagine the example. The plus or minus, what they're actually telling you is the margin of error. So here, if you actually figured out what that margin of error is, it's about 0.02. Basically, I mean, I'm rounding this, but it's about 0.02. But that plus minus, anytime you see them put the, and actually they don't say 0.02, they keep everything in percentages, right? What they're really telling you is that margin of error. So whenever you like see polling or any election coming up right now, it's not, I guess, as big as the presidential one. When you see all these reported numbers, they're telling you the sample proportion, and then they're also telling you that plus minus, that's your margin of error. So you could actually back out when they put that information out there, what the confidence interval would be. And then you could actually make the prediction of which candidate is going to get a higher amount of the popular vote. Now, you'll be right 90% of the time, but we might have ended up with skewed samples, and we're going to be wrong 10% of the time making these predictions. But, you know, never going to be 100% in everything unless we pulled every single person in the United States. We can't do that. All right, so anytime you don't have an overlap here, you could say that that one group, or in this case, the proportion of people voting for Clinton is going to be greater. Does that make sense? Questions on that?
Where did the 2% come from?
So, yeah, it's a good question. So I was just saying, when they tell you this, like on the news or whatever, what they're really telling you is your margin of error. And hopefully I didn't erase it, but I think I did. What did I say the margin of error was earlier? It's just that Z value times that standard deviation. So our Z value is 1.65. Well, our standard deviation is 0.0143. I'm rounding really back, so I'm just going to the second decimal here, but that would be about 0.02 for that plus or minus 2% that you might see like when the media is putting it out there. They, just like we do in everyday language, they always show things as percentages, but when we calculate, we're kind of doing it based on proportions. And then, you know, we kind of convert that. The reason why you don't, not to go too inside, because I'll give you an explanation. The reason why we have to do proportions and then at the end convert them into percentages is because if we put percentages in here and we're squaring things, it's not as simple as just being able to use the percentage values and come to the same answer, because when you're taking the square root, you know, moving the decimal 2 places actually should be 4. And so when you're calculating the confidence interval, you need to do it in terms of proportions. And then if you're the media, you then can turn it into percentages to make it easier for people to kind of digest. I'm not going to make you guys do that. I was just trying to relate it to something that you might see. Any other questions on here? I just had some other polling data I thought was kind of interesting, because like this was Reuters, and this was another popular one. It was a little bit larger of a sample size, and there I was trying to predict the election for everyone before it happened last time, but there was a little bit of an overlap. You know, you kind of see 0.492, which is barely above 0.4888. But we all kind of know the outcome in terms of one popular vote. So it looks like This is a little bit more of an accurate sample. But what's interesting is, I can say this at 90% confidence. So another point I want to make before we go to Excel is, well, what if I wanted to be able to predict this election with 99% confidence? What could happen, right? Well, the only thing that's going to change, I'm going to have the exact same polling data, or the same survey, so the same sample proportion, same sample size. If I want to say with a higher level of confidence, what's going to change?
Your margin of error becomes bigger.
The margin of error will become bigger, but why? Because when I want alpha over 2 in the tails now, at the 99% level, alpha is what, 0.005? 0.01 divided by 2. Well, before, remember that 1.65, that corresponded to 0.05. So in order to get that smaller area for the 99% level, 0.005 in the tail, what's going to happen to my z value? So this is negative. It's going to have to become a larger negative value or larger absolute value. So then when I plug the z value in here, I'm going to have a bigger value, making my margin of error larger, which will make my confidence intervals wider, right? Adding and subtracting a larger value. So at the 99% level, I'm still going to be basing these off those same sample proportions, but my upper and lower bound are going to go out a little bit wider. And so sometimes when I want to say things with a higher level of confidence, well, now what happens? I've got an overlap. Why can't I now with 99% confidence say that Clinton's going to get a higher proportion of the vote? Well, because it could be that the true population proportion for her is here. And it could, or I said Clinton. This was I went back to 2016. Joe Biden. I'm having a Joe Biden moment. So, right, the proportion of people who are going to vote for Biden could be here, the proportion of people who are going to vote for Trump could be there, in which case Trump would have a higher population proportion. But it could be that Clinton was over here, or Biden was over here and Trump was over here, in which case, Biden would have a larger proportion. So anytime there's overlap, I just can't say it. I can't make the statement at the 99% confidence level. Is that any questions on that idea? So anytime I say things with a higher level of confidence, it was widen my confidence intervals, making it more likely I see an overlap. And it's always easier to say things at lower levels of confidence. Right? So we'll go through kind of how we would do this in Excel, and then we will go on to the next type of confidence intervals. So we'll come back to this. I added some data to it. So if you're wanting to work along, I added some additional data to this. So I put up this file on Canvas called median rental price in class. I'll update it after class. That has everything that we're going to work on kind of reflected. But I don't know. I think it's helpful to work along, trying to make sure you know how to do this in Excel. I'm not going to give you another Excel assignment. We have that current Excel assignment. So some of this you'll have to apply to that one. So it might be a good idea to kind of go through it. So we did this last class where we built the confidence interval for what? This was rental prices, right? So we're going to do a very similar thing. Let's say, I'm going to make this a little bit wider here. I'm going to add in this column, which is the rental price being over $2,000. Okay. So you're not going to have to use what I'm about to show you on the next Excel assignment. If you had a variable in there, it's already going to be 10. But we're going to use this kind of down the road. So I'm just going to introduce it now, right? So there's a formula in Excel called the if formula, or the if statement, right? Well, basically, I want to create this other column, this other variable. That's a 1 if the city has rental prices over $2,000 on average, and a 0 if they don't, right? So what am I trying to test? I'm trying to test for whether or not this observation or this city has an average rental price over $2,000. That's what I'm wanting to check to see if that is true. Excuse me. If that is true, well, then that variable should be a 1 because that variable is supposed to represent whether or not the city had over $2,000 average rental price. If that's not true, comma, I want to put a 0. So the way that we'll do this if statement is what am I checking to see if this is true? then comma, if it is true, put this value, comma, if it's not true, put that value. And like, as I was typing this out, Excel kind of reminds you of that order. And like I said, you won't have to use that part on the next assignment, but we'll use it kind of down the road. So I wanted to introduce it here. And then a nice quick shortcut. If I double left click when I get this black plus sign, I don't have to drag this all the way down. I can just double left click and it will copy it all the way down to the very last observation. So that's kind of a nice kind of little shortcut there. So I now have this 1, 0 variable, and I'm just going to copy this and paste it down here instead of typing all these numbers in again. But basically, I'm going to want to find the Z value and then find the lower and upper bound. But now for the proportion of cities that have rental prices over $2,000. Okay. So what I'm going to do, and actually, before I do this, I need to create a little bit more room here. I'm going to move these down just to give us a little more room to do some work right here. So I'm going to need my sample proportion, right? That's one of the things I needed. I'm also going to need my sample size. So hopefully we remember, how do I find my sample size? This was simply the count function, right? Then go up here. Now we already had it from our previous work, but just in case we did, if we didn't, Control Shift, Command Shift on the Mac, hit the down arrow, hit Enter to come back to the cell. I've got my sample size. To find my sample proportion, we said the sample proportion is just a unique case of the sample mean when we have a 1, 0 variable. Well, we have a 1, 0 variable, so all we want to do is find the mean of it, which is that average function in Excel. So average, Control Shift, Command Shift on the Mac, hit the down arrow, hit Enter to close that parentheses, go back up to the cell. I've now got my sample proportion of my sample size. So of these cities, about 27% of them had rental prices on average over $2,000. Right? Hopefully you're feeling a little bit more fortunate to be living in Muncie right now. I hate saying that. So based off that sample proportion, I want to build kind of a confidence interval for the true population proportion is. So the only other thing I needed was these Z values. There's nothing new here. This is exactly the same. I mean, we were looking them up the table the same way as we were for the sample mean when we worked through these by hand. So we're going to use the exact same formula that we did for that sample mean when we were looking at those Z values. We know the area we want in the tail, alpha divided by 2. So if we know the area in the tail and we're trying to find that corresponding Z value, we're working in reverse or the inverse, right? So what probability, what area do I want in that tail, that lower left tail? Alpha divided by 2. Now, what's the problem going to be when I hit Enter here? Because I'm looking at alpha over 2 is that smaller value in that lower left tail. When we did this by hand, we said we were always going to find the number of standard deviations we wanted to go below or the negative value. Well, when I actually enter these formulas into my, the lower and upper bound formulas, I just need to know the number of standard deviations away. So I'm just going to use that ABS or that absolute value function. So it just drops that negative sign, just gives me that number of standard deviations away I need to go. Okay. Questions or anything up to this point? So now when I copy this down, I'll get the number of standard deviations for each of these different confidence levels. I don't remember. I think I was just showing you could do this with any level. Well, you won't usually use 87.5, but just kind of an additional example to show we could do any level of confidence. So then to get my lower bound, well, this is where I probably could do an intermediate calculation to make my life easier, right? Instead of trying to plug this whole formula in here, I'm going to calculate that ahead of time, so then I just have one value, right? So that standard deviation of our sample proportions, let's see, I'm going to make this a little bit wider so we can kind of see what I'm doing here. Well, maybe. There we go. It's actually, there we go. Make this one a little bit wider so you can see what I'm doing here. So we'll use that square root function. What do we want to take the square root of? Our sample proportion. So I just clicked on that times 1 minus that sample proportion, just clicked on it again, and then divided by my sample size, right? see if I can get this on one line here for us. Okay. So now I'll have that intermediate step kind of out of the way. Now it's just a matter of using Excel to be our calculator. To get my lower bound, I want to take my sample proportion, subtract 1.6448. I'm going to be a little more precise now, standard deviations. Well, that's just the number of standard deviations where I need to go. I then need to multiply that by whatever that standard deviation is of the statistic I'm looking at, which is now the sample proportion. Okay. Now, if I copy this down, I think we did this last class, the problem is going to be, I do want that z-value to update, but when I'm building different confidence levels, my sample mean, my sample proportion, my sample sizes, those don't change. So those cell references that I used for the sample proportion and that standard deviation of my sample proportion, I don't want those to change. The only thing I want to update when I'm building different levels of confidence or confidence level intervals at different levels of confidence would be that z-value. So that's the only thing that I will kind of leave unfrozen or without dollar signs. Okay. I'll then drag that down. I've now got my lower bounds here. Okay. Notice when I start to say things with higher levels of confidence, that lower bound keeps getting lower and lower. Now, I think I also showed you this with the sample means. Instead of typing this all in again, I'm just going to double click on that cell and highlight that formula. I'm going to copy it. Easy way to get out of Excel, because if I start using my arrows, sometimes it'll put in cell references. I'm just going to hit enter. All right. I'm then going to double click over here and paste, and it won't update those cell references. And the reason why I did this is because I know that to get the upper bound, I wanted the exact same equation. The only thing that's different is I add the margin of error. All right. So I just have to change that negative to a positive sign, drag that down. Now I've got my 3 confidence levels. All right. So it's pretty similar to what we were doing before. I mean, there's no new formulas in Excel other than the fact that we're using a different formula when we're having it do that math for us, right? But the actual built-in function's exactly the same as before. Okay. And you can kind of imagine, like, let's say someone says, oh man, a third of homes have rental prices, or a third of cities have average rental prices over $2,000. Well, I could look at them and say, based off this pretty big sample that I took, right? No, right? The actual proportion of homes that have above $2,000 average rental prices, somewhere, a little bit lower at the very worst, a little bit lower than 30%, right? Somewhere in this range of values from 0.24 to 0.29-ish. Okay. Any other questions about Excel? You want to see a cell again, or why I did something the way I did? We're okay with this. Okay, before I forget, let me save this. Okay. So that's good. Right. We've got our proportion confidence intervals. Really shouldn't be anything too terribly tough. All right. So the next thing that we're going to do is we're going to build confidence intervals. I kind of told you, how were we built? How did we have the population variance before when we didn't know what the population meaning was? Right? I said, maybe there's chemistry or the physics, you can know the machinery's variance, but more likely than not, you're not going to know the population variance. So before we had, sorry, I'm jumping classes. Before we had something that looked like this, where we had the intermediate step, we could calculate. So that was my confidence interval equation before. When we don't know the population variance, we're going to do the exact same thing. We're just going to notate that the standard deviation is a little bit different now for my sample means. And we're going to use an S instead of sigma. That kind of notates that when I'm calculating the standard deviation of my sample means, I'm now using a sample variance instead of a population variance. Okay. But there's a problem with this. Okay. And the problem is, if I use this standard deviation, right, for my sample means, and I try to convert different values into z-scores, they're no longer going to be standard normally distributed. I'll give you a little bit of intuition behind why. To really get the exact reason, you have to look at the mathematical proof. It's not necessarily that clear or even interesting, but you can prove that using that sample variance, would give me something that's not quite standard normally distributed. It'd still be normally distributed, but there's a problem. If I'm dividing, right, what was the difference between calculating the population and the sample variance? Yeah, we divided by n for the population, and then n minus 1, we were calculating the sample variance. So even if we had the population data, even if our sample was relatively large, that sample variance is going to be a little bit off, right? Because we're dividing by a smaller number. So dividing by a smaller number, it's almost like it kind of overinflates that variance. Now, there's a reason why we do that once we get to, a little bit in hypothesis testing. We won't talk about it before the exam in respect to hypothesis testing, but then for linear regression as well. We want to make sure having a larger variance, we're kind of erring on the side of caution, okay? And that'll make more sense, like I said, when we address some issues down the road. But for now, all we need to know is that because we're using the sample variance, it's no longer going to be that my sample means have this nice standard normal distribution when I turn them into z-scores, when I subtract the mean, divide by the standard deviation. But instead, they're going to come from a different set of distributions, which we call the student t distributions. Okay? So, kind of already mentioned, at least in terms of calculating the standard deviation of our sample means, it's just as easy to just replace the population with the variance with the sample variance. The problem is we're going to have to, instead of looking up a z value to give us alpha over 2 on each tail, we need to look up a student t value to give us alpha over 2 on each tail. Now, it's the same concept, right? The distribution, in fact, is actually really similar to the standard normal. It's just that it's got a higher variance, so it's a little bit more spread out. Okay. How much more spread out is it? Well, there's not one student t distribution. There's actually technically an infinite number of them. At every single different sample size, dividing by n minus 1 instead of n would create a different variation in that sample variance, right? Dividing by 1 instead of 2 creates a much bigger difference than dividing by 999 instead of 1,000. Yeah.
Is that bottom one right there the distribution formula?
This?
Yeah.
So this is going to be how we build confidence intervals. So just like we were doing before for sample means, but when we only have the sample variance. So it's still confidence intervals. It's just that now I only have a sample variance, which means when I'm looking up the number of standard deviations the way I need to go, before we were looking it up from the standard normal table, we're going to have a different table we have to look this up on now. And it's up on Canvas, and I'll show it to you in a second. So they're a little bit more spread out. So what that's going to mean, use some colors here. Might be jumping the gun a little bit, but I think it's relevant to where we're talking. So let's say if I was putting the z and t values now on the same axis here. So here's my standard normal distribution, just to make a point. I think if we look this up in the table, this area would be 0.025 at the area to the right of 1.96. Well, if our student t distributions are a little bit more spread out, then if I still want alpha, like the alpha over 2 value, 0.025, I still want that area in each tail. The problem is if I use 1.96, I'm really going to draw this exaggerated. But let's say this was my student t distribution. It's a little bit more spread, a lot more spread out the way I'm drawing it, but just that's to kind of get the idea behind what we're going to do. So it's more spread out, higher variance, which means it's going to be flatter, right? Seeing values far from the mean are now a little bit more likely. Well, now if I keep using that same 1.96 value, what's true about the area to the right of it under my student t distribution curve? It's much, much larger, right? So what am I going to have to do in order to get there to be 0.025 in the tail? The t value I need is going to have to be higher. So we're going to have to go a higher number of standard deviations away to guarantee we're getting alpha over the 2 in the tail for these student t distributions. So I think I'll come back to this in a second. I'll show you this here. I try to, put one in the slides. It's not quite as clear that there's a much larger area. You can imagine, if I looked at 1.96 here, for that standard normal distribution, the area under the curve, that's 0.025. Okay? Well, then if I use that same 1.96, the area under one of the blue and the green curve, much, much larger. So I'm no longer getting alpha over 2 in the tail if I keep using those same values I was using for those standard normal distribution, or the examples where I was either dealing with a proportion or the examples where I had a sample mean and a known population variance. So a couple other things I want to point out is, so I said that there's not just one student T, there's a different student T at every sample size, right? So as my sample size gets larger and larger, the student T distribution starts to look closer and closer to a standard normal distribution. And it kind of makes sense. Like as my sample size goes up, I'm getting closer to the population, right? What we're going to call, or the way we're going to identify what student T distribution we're using is called the degrees of freedom. All it is, and it seems kind of dumb, why don't we just use the sample size? Once we get to linear regression, there's a reason why. But this degrees of freedom is going to be n minus 1. So just the sample size minus 1. So if I take a sample of 100, my degrees of freedom is 99. Okay. So it's also symmetric. I said it's normally distributed. It's not standard normally distributed, but it's normally distributed. So the mean is equal to the median, which is 0, right? We've demeaned it. It's just a little bit more spread out. Now, when we look at the table, I'll kind of show this to you, but if we can get to pretty large sample sizes, really anything over 100, we get pretty close approximations to a standard normal. So it's really just these smaller sample sizes under 100 that we really have to worry about using the student T distribution. But most of the examples that we'll work through probably sample sizes less than 100 because that's really when you're going to have to use the student T. Yeah. So here, as the sample size gets larger, right, it gets closer and closer to a standard normal. So as my degrees of freedom, my sample size gets larger, notice that distribution is getting closer to my normal. Okay. Questions here before we can move on. So this is what the table looks well. I don't know why I use this truncated version. I'm going to show you the actual table. So here's that student T table. Now, one thing I'll kind of tell you right away, if you print this out or as you're looking at this, ignore this alpha symbol here. This is not the same as the alpha that we're using. All alpha represents in this table is the area you want in the tail, okay? And it kind of reminds you of that up here, right? So what this table does, it works the exact opposite of the standard normal table. With the standard normal table, our row and column headings were the z-value, probabilities in the middle were the corresponding area in the tail. Okay? Here, the values in the middle are going to be our t values, and then these column headings, that's going to be the corresponding area in the tail. So it's almost like they're flipped, right? In terms of what's on the column headings versus the numbers you see in the middle. So the way I would read this table is, on the left-hand side, my row headings, these are all my different degrees of freedom. So let's say I took a sample of 15, size 15. Well, my degrees of freedom would be n minus 1. So 15 minus 1 would be 14. And let's say I wanted to build a 90% confidence interval. Well, how many, standard deviations away do I need to go, or what t-value would give me that 90% confidence interval? What 90% alpha is what? 0.1. But remember, I need to look up the area that I want in one tail when I'm going to the table. So half of alpha is 0.05. So at that degrees of freedom of 14, well, I skipped it already, didn't I? I go to that area I want in the tail of 0.05, 1.771, which, well, we don't have it up here, but remember, before we were doing examples, the number from the Z table was 1.65. So that T value that we need is a little bit higher than it was before. Yeah.
So you take your degree of freedom and then you find alpha divided by 2 and
Yep.
you in the middle.
And that's the T value or the number of standard deviations away you need to go to get that alpha over 2 in the tail. Yep. Exactly what it is. Any other questions? So one thing we'll notice is as I'm getting larger degrees of freedom, so let's say I keep looking at this 0.05 column. As my degrees of freedom get larger, my distribution should be getting closer and closer to a standard normal. So the T value I'm using should be getting closer and closer to that standard normal value. So notice this is approaching 1.65. If I were to get an infinite sample, in fact, that would exactly be standard normally distributed. Because if it was infinite, I have to have the population data, right? I've got everything. Now, we never have samples of any of it, but kind of notice here, at 1,000, we're only off like the third decimal. In fact, this is rounded, but I think it's out only like the fifth decimal, just because it's rounded, it looks even closer than it is. So when we get really, really large sample sizes, notice this table starts making pretty big jumps after 60. Because for these sample sizes, I mean, you could really use the standard normal values to get a pretty good close approximation, right? And we can't have every single value. This table would be way too long. Now in Excel, we don't have to use the standard normal to approximate. We've actually got functions that can look up any degrees of freedom or any student t-distribution for us. Okay? But if we're doing it by hand, we're kind of limited to these degrees of freedom. Now, I'll never give you examples like on the exam where I give you degrees of freedom of like 90, where you're in between. You know, it's going to be one of the values that are in this table. Okay?
You take information by or just back by the line.
Yep, just look it up. Yeah, so let's actually, I think that should give us everything we need to kind of work through a problem with some actual values. Okay. Oops, there we go. So that looks pretty similar to what we're doing before. Just use the sample variance and the population variance, and now we have to use a different distribution. So steps look exactly like they did before. Once again, we're just using the sample variance, so the notation changes a little bit, and we're using that student t distribution. Right? But these are the steps that we're going to use to build our confidence interval. So the same steps as before, just like I said, using the sample instead of the population variance, and using that student t distribution. Okay? Hopefully you can kind of see like these are similar. Right? So I'm going to skip this one because it doesn't have any context. It's not as interesting. And if we have time, we'll come back to it. This one's a little bit more interesting. So let's say I was looking at mean physician starting salaries, and American Medical Association puts something out, says, look, come be a physician, average starting salaries are 175,000. I look at that number and I'm like, I'm suspicious, right? So I take my own sample of 81 physicians and I find a sample mean of 160,000. And my sample variance is really large. 324 million? Yeah, 324 million. So based off my sample mean, I'm going to build a confidence interval, the alpha of 0.05, for where that true population mean starting salary lies. Now, an alpha of 0.05, what confidence level am I building?
90%.
Not quite. So you gotta be careful, right? Alpha, yeah, always represents the area outside of our interval. Okay. So it's out in decimal form. So there's 0.05 outside the interval. That's 5% outside, which means we've got a 95%. So remember, we have confidence levels and their corresponding alphas. 99, well, there's 1% outside, so alpha is 0.01, 95, 0.05, 90, 110. Now, when we go to actually build the confidence interval, what's going to happen? We're going to have to take alpha and divide it by 2, right? So even though we have alpha here, when we're looking up the number of standard deviations we want to go from that student t distribution, we want to go a certain number to the left and to the right, such that alpha total is in my tails. So there's a total of 0.05 of these two tails, or half of alpha in each tail. So 0.05 divided by 2 is 0.025. Okay. So I've got everything I need now. I kind of look over there to plug in my equation. I got my sample variance, my sample mean, and my sample size. I just have to look up this number of standard deviations where I need to go with this t value. Now, I've got the area I want to tail. What's the other thing I'm going to need if I have to use the student t distribution? Because I only have a sample variance.
81.
Need my degrees of freedom, which is n minus 1 or 81 minus 1. So 80. So I now go to my student t table, or student t distribution table, however you want to call it. And I wanted an area of 0.025. So I'm in this column. Scroll down here. Degrees of freedom of 80. So 1.99. Right.
You have to divide the alpha by 2 to find the thing in the chart every time as well.
for confidence intervals, right? If we're gonna end up using this for some hypothesis testing stuff, it changed a little bit. But you can kind of think about it as we're always looking up our area in the tail. Well, here, the area that we always have in the tail for confidence intervals is always half of alpha. Yep. So kind of think about here. We're at that equation. Once again, we can kind of break this down into steps. So if I'm plugging all this in at what, 160,000 plus or minus, we just looked up that t value of 1.99. I probably would calculate this separately, so I could just have one value to plug in. So the square root of 324 million divided by that sample size of 81.
Why do you not have to subtract that by one?
Subtract this by one?
Yeah.
So when we're thinking about that distribution of our sample means, to come up with what the standard deviation of that distribution is, it's simply taking whatever the original variance was from what you sampled on. The problem is we can't see the population variance. So we're going to have a certain sample variance that was calculated, but it was still out of whatever our sample size was.
Isn't it for like every other calculation?
When you're calculating the sample variance, you divide by n minus 1. How can I explain this? So this, we're calculating now. Think about it as you're calculating the variance or the standard deviation of your samples. But that's using the variance you calculated from your sample. So aren't quite the same things, right? The variance you calculated from your sample doesn't represent the variance of your sample means. In order to scale that down, and there's not a great explanation I can give you other than you walk through the mathematical proof to show that every single time you look at the distribution of a sample statistic, it's the original variance here. The original variance that we were using is the sample variance divided by whatever that sample size is. You're just scaling that down. So like, oh, we don't have the portions over there anymore. Remember the portion we divide by n. The sample mean, when we knew the population variance, we were just dividing by n there. So when you're looking at the standard deviation of your sample statistic, you're just scaling down those variances by dividing by n. But I understand why it's confusing, right? Why am I dividing by n minus 1 here, but not here, right? So it's not a, like I said, you can think about it as the reason why we're dividing by n there is it's just scaling this variance down so that it'll represent the standard deviation of the variance of the sample statistic that we're looking at. But I know that's not great, but really the reason why, you could prove that with lines of mathematical proofs, but it's not necessarily an intuitive result. So. It's a good question, though. I mean, I understand why. Any other questions at this point? So, I mean, once we get to this point, right, it's just getting that plugged into our calculator. Okay. So maybe. Oh, there we go. A little delayed. So this is just everything that we have. Once I calculate the intermediate step, we get kind of a nice number there. So it's just a matter of adding that margin of error to my upper bound and subtracting that margin of error to my lower bound. So here I've got that the mean physician's starting salary, population mean, has to be somewhere between about 164 and 156,000. So if the American Medical Association started out saying that on average physicians start out making 175 with 90, I already forgot, 95% confidence here, I could look at them and say what? No, it doesn't. Right? Or no, it isn't. Sorry. Right. So I know that based off my sample, that true population mean is somewhere with 95% confidence is somewhere in that range. Right?
Where are you? So when I have everything up to 160,000 plus or minus 1.99 times 2,000.
Mm-hmm.
Where does the 39 come from?
39.
And you're subtracting from.
Oh, I'm just showing you that if you could break this down even steps even more. 1.99 times 2,000 is 3,000.
Oh, okay.
Yeah, so if you wanted to, like, I mean, I think this is probably, easy enough to get entered in there. But if you really wanted to, you could kind of break this down and think about what my margin of error actually is, right? So here, my margin of error is actually a good question because my margin of error here would be $3,980. Okay? Like, just like before, we had margin of errors for our proportions, we got margin of errors here for the sample mean.
Thank you.
Yep. Other questions on this? We keep going here.
So this is more about semantics, and I just never understand this. Why, even though when you calculate this, obviously you always multiply first. Why is it always written like that? Why is it not 2,000 times 199 plus or minus 260,000? Is that just your preference, or is that how it's normally?
So why do I write it on, why don't I write it on two lines like here?
No. So like, order of operations, you're multiplying that out first. Why is it always written vice
Oh,
versa?
so it's typically, if you see confidence intervals written out, they will write them out in this format. Because we're doing confidence intervals for like our basic statistics, sample means and sample proportions. They get a little bit more complicated, so you might even, you could plug in here, like, you know how the sample mean is like the sum of the x's over n, you could plug that in here. And for more, you know, as you go to more advanced statistics, you might actually have an equation that you're calculating that sample statistic that you're building it around. I would say probably where it really comes from is just convention, right? And it's the idea that it stems from the fact that what I'm really doing, right, conceptually, is I'm basing my confidence interval around that sample statistic. So that's why we write it as though it's the sample statistic minus my margin of error, the lower bound, and my sample statistic plus the margin of error in the upper bound. But you're right, I could find my margin of error and then just, I guess the trickier part about doing it that way is for the negative one, you would have it, I think this is what you're asking. Why isn't it written like this? Is that what you're asking me?
Yeah, like for example.
I think it's because you have to be a little more careful about remembering that you've got a negative sign here. But I think the real answer is because it lines up with what we're actually doing. We're actually starting at this sample statistic, adding a certain amount through your upper bound and subtracting a certain. But it doesn't matter how you write it, and if you're just thinking about the mathematics.
Yeah, I was just like, cause like, you could go about it the other way as well. If you have what you want as your margin of error.
Mhm.
And you're just, I mean.
So I would say, going back to that proportion example, maybe this makes a little more sense. So if I know that the sample statistic is like 46% or proportion of 0.46, it makes way more sense to report my margin of error next to it in terms of like, this is what we found from the sample. This is what you would use to then build your confidence interval. So the sample mean we found, the best guess of what we have the salary is going to be is 160,000. You want to build your confidence interval. This is kind of your margin of error. I mean, it doesn't really matter either way, but it's, yeah. And I think when we get to linear regression, I mean, the real honest answer is a lot of the times you don't even see this. A lot of the times all you see is the upper and lower bound. So it doesn't really matter how you calculate it. If you wanted to flip them, if it made more sense to you, by all means, go ahead and do it. Yeah.
I mean, it was just the practice of it. I didn't.
Yeah,
I didn't understand it.
Yeah, I mean, I think that it's preferred to do this, like I said, because it lines up with what we're doing, adding, subtracting from this sample statistic in the direction. Any other questions at this point? So. I think I'll show you guys how to do one of these in Excel, kind of write it up on the board at the same time, kind of how we would do this by hand. I think we got just enough time to do that. Okay. So go back to this Excel example or this Excel sheet. I'm going to go to this UFO sightings kind of data set. I found this the other day and thought it'd be fun to play around with. So let's go so you can actually see what I'm doing. So I've got this data of all these UFO sightings. I'm going to use this duration variable in seconds, just kind of the length of the sighting, how long they saw it. It's not going to be that meaningful, but it'll be just a good example to see kind of how it would work with some sample data calculating sample mean. So, oops. I'll need my sample mean, my sample size, and now I'll have to be calculating my sample variance as well. Those are the three components that I need, other than that number of standard deviations away I want to go, or other than that t-value. So this should be kind of old hat at this point, but to find the sample mean, I'll just take the average of that duration variable. Sample size, just the count of that duration variable, Control Shift, Command Shift on the Mac. And then finally, my sample variance, okay? So I'm going to expand this, right? Now I'm going to do all three of our, just to kind of give us an idea. I'll do confidence here, alpha here. Then we're going to look up that t-value, okay? So I've got the 90, 95, 99% confidence levels. Those correspond to alphas of 0.1, 0.05, and 0.01. When you're working on the Excel homework, you don't have to type these out if you don't want to, you can kind of put these in, in the equation. I'm just using cell references here to kind of show you how you could do it very quickly for 3. So really, I've got everything I need, right? I plug in whatever, 6,723 was my sample mean. I've got 41,922 UFO sightings and some astronomically large sample variance, but I would have those values to plug in. The only thing left I need to do is find that t-value that gives me alpha over 2 in the tail, okay? So when we were doing this for proportions, or when we knew the population variance, we could use that standard normal distribution. We knew the area in the tail. We wanted the corresponding z-value. So we use norm.s.inv. So we're still working in the inverse. We still know the area we want in the tail is alpha over 2. It's just now we're using the t-distribution. So the only thing that changes there, instead of norm.s.inv, t.inv, right? I've only got a sample variance. I have to use a different set of distributions, right? What area do I want in the tail, or what's that probability? Alpha divided by 2, comma, oops, remove this. Okay. But now I need one more piece of information, which is I need to know which student t-distribution I'm using. So this tells that, yeah, you're using a student t-distribution, but which one? Well, I need the one that lines up with my degrees of freedom, which here would simply be my sample size minus 1, okay? So this will do the exact same thing that norm.s.inv did for me, but it's using the student t-distribution. So I hit enter, I've got that t-value. Once again, it's kind of already built into our formulas, so we'll just kind of drop that negative sign by using the absolute value function. And then if I wanted to, I could pretty quickly kind of copy this down. Ooh, what went wrong? Well, I wanted alpha to update. Oh, well, my sample size should, oh, what did I just do? Okay. Control Z, there we go. But my sample size should always be the same, so I'm going to freeze that cell reference. Now, when I copy this down, it looks better, okay? And from here, it's exactly what we were doing before. I would probably go up here and calculate the standard deviation of my sample means, right? Just the square root of the sample variance divided by my sample size, right? That's kind of that intermediate step. You could do this all in one line in Excel if you want. You don't have to break it down to steps. You just got to be a little more careful with parentheses. So now it's just take my sample mean, subtract this many standard deviations to get my lower bound. Well, if that's the number of standard deviations where I need to go, what is the standard deviation? So I need to multiply it by whatever that standard deviation is, okay? Once again, if I want to copy this down, the only thing I want updating before was the z value. I'm still basing it on the same sample mean. I've still got the same sample variance and sample size. So I'm going to allow that t-value to update, copy that down. I've got my 3 lower bounds. I'll go back in, copy, enter it out of the cell, paste it over here. The only thing I need to change in the upper bound is that negative to a positive sign. Okay. So it's really the same process that we were using before. The only thing that really changes is this t value. Okay. Now we don't use z values anymore. We're just looking at t values. So we use the t.inv instead. Okay. Any questions at this point? A couple more things before we get out of here. So I'll save this. And this is, whoops, this will be the one that I put up on Canvas when I get back to my office after class. I want to point out a couple things before we kind of finish here. So one, these values look really, really similar to the z values I was finding. But why? Well, I've got a huge sample size, right? I said as that sample size gets larger, it's closer and closer of an approximation. Now, it's still an approximation. Like, this is not quite the same number as what we found here. It's a little bit off, right? But not by much, right? Now, the problem is if I had a much lower sample size, to kind of make the point here, let's say I found the same sample mean and sample variance, but I found it from a smaller sample size. Well, if I have a smaller sample size, what's that going to do to the standard deviation of my sample mean? Increase it. So I'm going to be adding and subtracting a larger number. So I should get wider confidence intervals, right? But also, I'm going to have to get different degrees of freedom, right? So my student t-distribution is now more spread out. So I'm going to have to go a further number of standard deviations away to get that same alpha, desired alpha over 2 in the tail. So notice now when it's based off a sample size of 35, the t value that gives me alpha over 2 in the tail, I mean, this is what, 2.72 instead of 2.57. Well, now they get quite a bit different, right? And we might not remember exactly what these were before, but I'll kind of use Control Z so we can compare it. Notice when I have a really small sample size, sometimes my confidence intervals are like really wide, right? But if I can get a larger sample size, that should make them more narrow. Notice here, much more narrow, allows me to kind of actually get closer, kind of pinpoint down where that population mean might be a little bit better, right? So larger sample sizes allow us to get these more narrow confidence intervals, which is good when we're thinking about, I want to be able to rule out certain values, right? So yeah. Any questions? So hopefully you're seeing like the process is like similar, just a little bit different for these 3 different scenarios that we have. We'll talk about hypothesis testing on Wednesday, and we'll finish it up on next Monday, and then transition to review on Monday. But basically, we'll be doing hypothesis testing for these same 3 types of examples. And as you're working on that Excel assignment, if you have any kind of questions, I will be around tomorrow, but I don't know if you want to schedule something, you have to shoot me an email. Otherwise, Wednesday and Thursday, like usual, 2 to 4. Okay. All right. See you guys on Wednesday.